So now that we know how to identify the degree of a polynomial function, let's apply that to what we call the power functions. We can see in this set of examples that I have right here that we have various polynomial functions, each having incrementing degrees for my polynomial. All of these polynomial functions, which are actually monomials, look like one term with a power, right? Okay, so that's kind of the definition that we have right here, talking about just a power function. And when we look at these power functions, let's look at this example of this set of polynomials that I have right here. In red, I have the function x squared. In blue, I have x to the fourth, and in green, I have x to the eighth. And what do you notice about these three functions? Well, they all have the same basic shape. They all look like a parabola or a quadratic function that we're used to seeing. As the exponent in my function increases, you can see that the graph of my function tends to get skinnier, so they are moving in towards the y-axis, or getting a little bit skinnier as we have them coming through here. You can also see that each of these functions are passing through the same two sets of ordered pairs here, -1, 1, and 1, 1. And then another thing you may notice is that they are flatter. They tend to get a little flatter down here in between those two numbers. Now, all of these functions, each of these three functions, are exponents raised to even powers. And this right here is a characteristic, or these characteristics are properties of what we would call an even power function. So here I have properties of x to the n, where n is a positive even integer. We could say that its graph is symmetric with respect to the x-axis. The domain and range of these functions up here would be from negative to positive infinity. And then the other thing that I think is the most important thing that I want you to recognize for this section is that when we have an even powered function, what is the end behavior doing here? What is the end of my graph doing? Well, in each case, no matter what the power was for my even powered functions, the end of my graph is going off to infinity on both sides, right? So the end of my graph looks like, so if I were to hold my hands up and make like a field goal sign, like a referee, that's what we're referring to when we have an even powered function. Both ends go up to positive infinity. Now let's look at this set of functions that we have right here. So I have x cubed, x to the fifth, x to the ninth. So since we just talked about the even powered functions, hopefully you recognize that these are all odd powered functions. They all are in general the same shape as my cubic function, which you should be fairly familiar with. Again, as the power of my function increases, the graph of my function tends to get skinnier. It gets closer to the y-axis, just like the previous one did. Notice, however, that for this function, the end behaviors are going in opposite directions. Okay, so we have one direction going to positive infinity, one going to negative infinity. And so for an odd powered function, the end behaviors tend to go off in opposite directions. Now the domain and the range would be the same no matter what we were talking about for my odd powered functions, but the domain in this would be all real numbers. And then we might want to be able to say that it would be symmetric with the origin. So in other words, if I were to rotate this point right here that I'm hovering on down over here, it would rotate to the point down here in the third quadrant, and we say that that is symmetric with the origin. These two ideas, where we have properties of even powered functions, and they go off to infinity in both directions. And we have properties of odd powered functions, which go off in opposite directions towards infinity, give us a general idea of what our polynomial function should look like when we first glance at whatever it is that we're doing.